many of the convergence tests we've looked at so far work on decreasing positive series. Now we're going to take a look at some techniques we can use if there are negative terms within our series. We'll focus our attention on something called alternating series. An alternating series is one in which the terms alternate sign. A canonical example of this is the series 1 minus 1/2 plus 1/3 minus 1/4 and so on and so forth. This is called the alternating harmonic series. Previously, we've seen the harmonic series 1 plus 1/2 plus 1/3 plus 1/4 and so on and so forth. And we've learned that that series diverges. Here we're going to explore how the alternating harmonic series may or may not behave differently. We'll start off by noticing that we can write the alternating harmonic series as the sum from n equals 1 to infinity of -1 raised to the n plus 1 power times 1 over n. It's the -1 raised to the n plus 1 power that's going to force the signs to alternate. Notice that that piece will be positive when n is odd, and it will be negative when n is even. As in all the series we've seen previously, we're going to focus on the partial sums of this series because the divergence or convergence of this series is strictly tied to whether or not its sequence of partial sums converges or diverges. This animation demonstrates what the partial sums do for this series. We can see that the first partial sum in blue is a positive number 1. The pink next to that then represents what happens when we add on the second term, which is negative. We see that the sum drops down. Adding on the third term brings the sum back up. The fourth term drops it back down. So in this animation, each blue term represents a partial sum that we get by adding on a positive term. The pink rectangles represent the sums that result when we add on a negative term. We can see that as we add more and more terms into our partial sums, they appear to be narrowing down around some value. If they do in fact converge, that is, the distance around our proposed value continues to get smaller and smaller and smaller, then we can say that this series converges. Our goal then is to understand under what conditions does an alternating series converge. It turns out that determining if an alternating series converges is fairly straightforward. Any alternating series of the form -1 to the n plus 1 times a sub n converges if its terms are non-increasing. In other words, a sub n is greater than or equal to a sub n plus 1, and if the limit as n goes to infinity of the a sub n's is equal to 0. Let's return to our initial example, the alternating harmonic series, and put it to the alternating series test. So if we look at each of the terms, they are of the form 1 over n. We know that n plus 1 is bigger than n for any integer n, which then tells us that 1 over n plus 1 is smaller than 1 over n. That means that our series is decreasing. A sub n is bigger than a sub n plus 1, so our series is decreasing. Our test told us that our series had to be non-increasing, and we've certainly achieved that if it's decreasing. Our last thing to check is the limit as n goes to infinity of a sub n, which in this case is 1 over n. We know that that limit is 0, so we've checked off the non-increasing requirement for our test, and we've checked off that the terms go to 0, so we can conclude that the sum from n equals 1 to infinity of -1 to the n plus 1 times a sub n converges. We'll find that we need some additional tools in order to actually compute the value of the series, but for now we know that it converges, unlike its non-alternating counterpart, the harmonic series. For our next example, let's take a look at the sum from n equals 1 to infinity of negative 1 to the n plus 1. This is just the series 1, minus 1, plus 1, minus 1, and so on and so forth. Now you might have some feeling that because every pair of terms cancels each other out, that the sum of this is going to be 0. But let's take a look at a visualization of the partial sums of this series to see what's actually happening. Here we can see that the partial sums bounce back and forth between 1 and 0. In order for the series to converge, the partial sums themselves must converge. In other words, we'd need to see a funneling effect in this animation like we saw in the previous one. So now we have some sense that this series does not converge. Let's put it to the alternating series test and see what happens. Recall that there are two criteria that an alternating series needs to meet in order for it to be convergent. The first is that the terms must be non-increasing. In other words, a sub n has to be bigger than or equal to a sub n plus 1. We know in this series that if n is odd, then a sub n is going to be negative 1 to the n plus 1 power, which is going to be an even number, which is going to be positive 1. And a sub n plus 1 is going to be negative 1 to the n plus 2 power, which is then negative 1. So in this particular case, when n is odd, we know that a sub n is in fact greater than or equal to a sub n plus 1. However, if we consider the case when n is even, then a sub n is going to be negative 1 to the n plus 1, which is going to be an odd power, which is going to be negative 1. And a sub n plus 1 will be negative 1 to the n plus 2, which is now an even power, and that's positive 1. So when n is even, we get that a sub n is less than, strictly less than, a sub n plus 1. So this is not non-increasing. So it fails the first part of the test. We can also see very easily that the limit as n goes to infinity of negative 1 to the n plus 1 does not exist. That limit itself is going to bounce back and forth between negative 1 and 1 as n gets large. So the limit is not infinity, it just merely doesn't exist. So this fails the alternating series test. And because the limit of the terms of this series is not 0, the divergence test tells us, in fact, that this series diverges. To wrap things up, we've developed a fairly straightforward way to determine if an alternating series, one whose terms flip-flop back and forth between positive and negative, converges if its terms are non-increasing, which means that each term is bigger than or equal to the following term, and if the limit of those terms is actually equal to 0.